Hello everyone. So welcome back to the latest lecture session. So we have in the last lecture session we were done discussing the aspects related to aqueous complexes, right, and the relevant applications. So we are going to move on to the next logical aspect, which is going to be precipitation and dissolution, right. I mean, let's just take a moment to understand what it is we are talking about. So obviously, let's say you have salt and you take a liter of water, a glass of water, and you add some salt. Initially you will see that everything dissolves, right. But if you keep adding or increasing the amount of salt added to that glass of water, I'm sure that at certain after certain level of or addition of this salt, you are going to start seeing that there is no more, the salt doesn't dissolve anymore. Whatever you put in starts precipitating out at the bottom of your particular container, right. So again here what are we looking at? We see that the solution holds the maximum extent of that particular soluble form of those salts possible, and once you reach the threshold, obviously, right, the salt starts precipitating out in the solid form. So here initially when we add the salt, they dissociate, right, and they stay in there, let's say relevant as relevant ions, right, in the solution. But once you keep adding the relevant salt, let's say at a certain threshold, the solution, you can say, that can't take the or hold these cations or anions anymore, and now you are going to see precipitation, let's say, right, or no further dissolution, right. So let's just try to understand what we are going to talk about here again. So two aspects here, precipitation and dissolution, right. So again, what's precipitation about now, right? It's the process of forming a solid compound from a soluble species, right. So again, understand that, I mean, we don't need to mug definitions up, right. This is just for your understanding. So we are talking about, or we are trying to understand precipitation as formation of solid from soluble species. So the example that I gave before isn't directly applicable here, but it helps you understand the system, right. So again, whenever you have a process that leads to formation of solid from soluble species, we call that the we refer to that as precipitation. And obviously dissolution, right, the process, it's the vice versa of your precipitation, right. Let's just get that down here. And obviously what is dissolution about? It's the inverse of this, more or less, right. So what is this going to be equal to now, or equivalent to the process of forming dissolved species or compounds from your solid here, right. Again, I mean, I guess that's pretty self-explanatory, right. Once you look at the term dissolution. So in one case you have solid being formed from your dissolved compounds, and the other the vice versa, more or less your dissolved compounds forming process of forming dissolved compounds from the solid, right. The solid forms the dissolved compounds in dissolution. Yes. So again, let's move on. Obviously we are going to discuss this in relevant detail over the next couple of classes or sessions, pardon me, right. So first we need to understand why is it that I am concerned with it, right. So let's look at the applications here. So obviously, right, what are we trying to achieve here by understanding this particular system with respect to precipitation now? First we look at some of the applications with respect to precipitation and then move on to dissolution, right. So again, precipitation, think of, before we go further in this particular aspect, think of what we discussed in the previous sessions, right, complex formation. So let's say when I put in, let's say, a metal, and in the presence of a ligand, which is an electron rich compound, you saw that a complex is formed, right. So to understand how precipitation occurs, let's say, think of this particular complex, let's say, with one central atom or the metal and the relevant number of ligands as a nucleus, let's say. Think of that as a nucleus, or let's say a monomer, let's say. So over time, let's say, as you keep increasing the concentration of the metal and the ligand, let's say, the concentration of the complexes or complex keeps increasing, and you have, let us say, a formation of, what can you say, a kind of a 3D structure with, let us say, if I call this initial complex a nucleus, right, the other complexes are going to be formed, let us say, around it, let us say, right, and let us say more or less going to be an arrangement in a 3D structure. So as this keeps going further, right, as this particular 3D, what shall I say that, call that, let us say 3D matrix keeps developing further. So the innermost complexes are now no more exposed to the bulk solution, right. So now what it is that we are trying to say is that when they are no more exposed to or in the bulk solution, what does that mean? They are no more in the dissolved or aqueous phase, they are now in a solid phase, right. So you can try to link the complexation, right, to your precipitation too, right. Initially think of that we have a nucleus wherein that considers where we are calling a nucleus to be one particular complex with one central atom or the metal and the relevant number of ligands. As we keep increasing the number of what do we say, or the concentration of complexes. So think of this is a complex, you have them developing all around that, various other complexes surrounding the nucleus, if you want to call that, right. And as this particular structure gets bigger, or let us say progresses further, the those complexes within the matrix, let us say, are going to be no more in the bulk solution, which was the aqueous phase earlier, right. So now let us say you are going to have or look at the initial stages of your particular precipitation, yes. Again, so again that is your particular understanding or how we are going to link that to the aqueous complexes, right. So here let us say we are talking about obviously applications here of precipitation. So why I linked that to aqueous complexes is whenever we looked at aqueous complexes, we always looked at metals, right. So let us say here in this case if I have, let us say, a metal that is toxic and I want to remove that from the solution, obviously what is it I can try to promote? I can try to promote its precipitation, right. So let us say I have a chromium, let us say, in its oxidation state +3, let us say, right, and why would I want to promote +3 rather than +6 form of chromium? Because +3 is more insoluble, right, or less soluble, so it will precipitate out. So I can promote formation of chromium and it will precipitate out as CrOH thrice, right. So again one certain application is obviously the removal of toxic metals, right, and examples as we just talked about, CrOH thrice. So I am going to use this particular subscript, right, to indicate that it is a solid, right. Lead 2, let us say PbCO3 if I want to remove lead, right, and also let us say if I want to remove mercury, right. And if people can remember that we looked at an example where we looked at complexes of mercury and sulfide, right. So now obviously here we see that mercury and sulfide, right, the complex it is a natural progression to the precipitation of mercury here, right. So again keep that in mind that precipitation is one of the most widely used methods obviously for precipitating out or removing the toxic metals from your particular solution. So obviously what do you need to add? You need to add the relevant concentrations of your ligand, right. So the ligand, if it is OH minus, obviously what does that mean? It means changing or varying the pH, right. So that is obviously remarkably relevant in this particular case, but in general CrOH thrice precipitates out at most pH, but let us say for example it is PbCO3, let us say, right, and what is the role of pH here? So now we need to dig back into our acid base relevant knowledge here, right. So as you know, right, CO3 2 minus can also exist as HCO3 minus and H2CO3, right. So obviously for Pb 2 plus and CO3 2 minus, right, in general we write this as the dissolution reaction, right. For this particular reaction from right to left to proceed, you need to have relevant high concentrations of CO3 2 minus, right. So obviously when will CO3 2 minus exist in solution at relatively high concentrations? Only when the pH is relatively high, right. Otherwise if it is at neutral pH or in that particular range, as you know HCO3 minus is going to be predominant and thus you are not going to have relatively high concentrations of the relevant compound which is CO3 2 minus. So again as we keep progressing further, you need to understand that each and every aspect that we have discussed earlier work in conjunction as an acid base, aqueous complex and precipitation. As in, let's say if somebody asks you what's the concentration of lead, let's say, you can't just look at this particular equation now, and let's say I can have the equilibrium constant for this particular equation, and that's going to be equal to activity of lead, right, and activity of CO3 2 minus, and activity of solid, which is equal to 1, because activity of solid, pure solid, is 1, right. Again, I can't just directly calculate it from here. Why is that? Because you know that it can again form complexes, right. So it's going to be linked to those particular aspects too, right. Pb2 plus can form complexes too, yes. Again, so keep in mind that they are in equilibrium, or it's a fine balance between all the three aspects that we have discussed thus far. So again, we are just trying to look at those particular aspects and how acid base relevant chemical processes are relevant here, PbCO3 and so on. So let's move on. What else can we look at, let's say. So another aspect that people obviously look at, or I'm sure everyone came across, is removal of hardness, right. So your groundwater, at least in around here in Roorkee, is remarkably hard. As in, what do you mean by hard? You have these bivalent cations, right, Ca2 plus and Mg2 plus. So how do I remove them now, right? So here we have hardness removal. There are different methods, but almost all of them, what is the principle here? It's precipitation, and precipitation in the form of CaCO3 solid and MgOH twice solid, right. So again, as you see, calcium carbonate, it can precipitate out. So again, what's the requirement here? Obviously you need to keep the pH high. Why is that? Because if you don't keep the pH high enough, CO3 2 minus would exist as HCO3 minus, I guess, right. So CaCO3 again, and the relevant acid base process, and again MgOH twice, again depends upon pH. As you can see, the higher the pH, the greater the concentration of OH minus, thus the greater the tendency to form the solid, right. So think of this again, what we just mentioned here. So let's say MgOH twice, the solid is going to be in equilibrium in your solution with a certain concentration of Mg2 plus and a certain concentration of OH minus, right. So as I keep increasing, let's say this particular system is at equilibrium right now, right. If it's at equilibrium, right, and I keep increasing this particular variable, or the concentration of OH minus, what happens now? So it's no more at equilibrium, right. The equilibrium has shifted now, and so again the system wants to what do we say, reach equilibrium, yes. So what's going to happen again? The reaction from right to left, right, it's again based on the Le Chatelier's principle, yes, that Mg2 plus would again what do we say, react here with, what is it now, 2 moles of OH minus, and then precipitate out in the form of MgOH twice, right. So again, that's the key here. Obviously if you want to promote precipitation, you want to increase the concentration of the relevant ligand, which in this case is OH minus, right. So what else now? We looked at removal of toxic metals, widely used, hardness removal, widely used. So I guess people also look at it for phosphorus removal. So phosphorus is a nutrient that you want to remove from your particular wastewaters, let's say, before discharging that into surface waters. Why is that? Let's say excessive availability of this particular nutrient along with nitrogen, let's say, can lead to an algal bloom, right, and that can lead to eutrophication, right, and the relevant effects, and I'm not going to go into that obviously. So there are biological processes that can assist in removal of your particular phosphorus, but obviously we can again we have chemical process too, whereby you can precipitate out phosphorus, right, and some of the forms in which we can precipitate them out are CaHPO4 solid, LPO4 solid, and FePO4 solid. So here more or less what is the PO4? PO4 3 minus, right. So it's more or less a ligand, right. Here you want to remove the ligand, right, unlike removing the metal earlier. Here you want to remove the ligand. So what do you need to add now? You need to add an electron poor compound or electron deficient compound, right. So what is it that we are adding? We are either adding calcium, aluminum, or ferric, right. So that's what we are doing in this particular case again. So again, this is obviously linked to your aqueous complex based chemical process, and again the next further or next logical step, which would be your precipitation. So the next aspect we are going to move on is we also need to, let's say, people look at iron and manganese removal. Right, and in this case we can remove ferric in the form of FeOH thrice, right, and manganese as MnO2, let's say, right, and thus applications of the applications of FeOH thrice precipitating out are remarkable. So think of where is it that we come across applying this particular principle of precipitation of ferric hydroxide now, right. So people might remember that you would come across ferric at least in your water treatment or sometimes in wastewater as being used for coagulation, right, or a coagulant, right. So again here if you remember, I guess one of our initial what do we say examples we looked at was where we had a CETP, right. If people remember that at one of the first classes, I believe, or the second class of this particular course, we talked about CETP personnel, and he was adding a source of Fe2 plus, right, Fe2 plus as his coagulant, and his reasoning being that it's in general cheaper, and he didn't believe that there was great deal of difference in the mechanism with respect to either addition of Fe2 plus and its action as a coagulant, or Fe3 plus and the relevant actions as a coagulant though, right. But here let us say in general in that particular case, keep in mind that these are industrial wastewaters, right. So and Fe3 plus, let us say, right. So we are just going to discuss this particular case, right, and where let us say the removal of Fe3 plus in the form of or precipitation of Fe3 plus in the form of FeOH thrice, right, is going to play a relevant or important role here, right. So keep in mind that we have Fe2 plus, right, and we looked at it, looked at the complexes formed at different pH, if you remember, in one of our a couple of sessions ago, pH 3, 7 and 11, and we saw that Fe2 plus stays as Fe2 plus at pH 3 and pH 7, and only at relatively high pH does it start forming Fe and OH complexes, right. We looked at that particular aspect, yes, but we saw that for Fe3 plus more or less at almost all the pHs it forms the Fe3 plus and OH minus complexes, right. That is something that we understood when we plugged in the relevant values in VMinTech in a couple of sessions ago, right. So here again we are going to try to use the same principle here. Let us say I am going to first demonstrate the formation of what is it now, a precipitate when we add either Fe2 plus or Fe3 plus, and I believe the case I am going to look at is a pH at let us say 7, okay, and one case is when I add FeSO4 which is source of Fe2 plus at let us say 1.5 millimolar, which is what people generally use in the common effluent treatment plant, right. And also the other one I am going to add let us say a source of ferric, let us say in this case I am just going to take the example of FeCl3, source of ferric Fe3 plus, same concentration of 1.5 millimolar, right. But unlike the previous sessions when we did not consider precipitation as feasible, right, here I am going to consider precipitation as a feasible process. So now let us understand or try to see how the system changes or varies here. So let us say again we are going to look at pH 7. Initially we are going to plug in Fe2 plus at 1.5 millimolar, obviously SO4 2 minus 2 will be at 1.5 millimolar. So in the second case I am going to plug in at pH 7 FeCl3 with Fe3 plus at 1.5 millimolar, so the Cl total will be 3 times 1.5, so 4.5 millimolar, I guess, right. So let us plug in those values and let us look at where we are going to be. So we usually maintain the pH at 7, let us say, right, and I am going to plug in Fe2 plus initially, Fe2 plus, right, and I am going to use units of millimolar, right, and the concentration let us say we just mentioned that it is going to be equal to 1.5, right, and it is 1.5, right, and I am going to add that to the list, and now SO4 2 minus at the same concentration because I am putting in Fe2 plus in the form of FeSO4, and where is that? Okay. Is that the only case or do we have anything else? S2 minus SO4, S as SO4, S minus 2 oxidation state, so on, S2, and this is SeO4 2 minus, not SO4 minus 2, so I am going to skip that. Okay, here I have SO4 2 minus, and I am going to add that to my list. I need to view edit my list, right? Okay, and I am going to go back to the main menu, and here though I am going to plug in, put in a few aspects that might not be remarkably apparent here, but what I am going to try to do now with Vimitech is I am going to specify that precipitation is feasible, right? How do I do that? As in, I need to specify possible solid phases. So here Vimitech will give an option to add possible solid phases. So I can add multiple solids, right? But obviously it's going to be time consuming, and I do not know, let's say if at this stage I do not know what Fe2 plus can precipitate out or in what forms it will precipitate out. Obviously Vimitech can help you by limiting, I tick this up here, take this particular option here, or consider this option to those species that can be formed based on the components that have been defined, right? So because I identified Fe2 plus, so here they says it's FeOH twice amorphous and crystalline and melantorite, I guess, right, if I pronounce that right. So in general, initially you will have amorphous formed first, we will discuss that later. So I am just going to say thus the amorphous form of Fe2 plus can precipitate out, and I will add that, and I will go back to the main menu, and now I am going to run Mintech. Okay, obviously again we look at different what do we say species here, which is what we expect. Again, the major aspect is that Fe2 plus is mostly present as Fe2 plus, it is 1.3 into 10 power minus 3. If you remember, we put in I think 1.5 into 10 power minus 3, and keep in mind that Fe2 plus stays as Fe2 plus for what is it like 80% maybe or 90%, God knows, right, 1.3 by 1.5 into 100. So anyway, that is fine, I guess. So most of it keep in mind stays as Fe2 plus, and we have relatively little formation of what do we say, the relevant complexes here, right, either in the form of FeOH, FeSO4, OH thrice, and so on, right. Keep in mind that the complex formation or the concentration of the complexes is almost negligible. But here I am not looking at complexes, I am trying to look at amount of solid that is going to be formed, let us see. So how can I look at that? Species distribution, will that really help me? Not really, it just says 85% stays as Fe2 plus, right. So that is it, I can't see anything related to precipitation here. So I am going to look at, let us say, equilibrated mass distribution here. So here it gives me an idea about what is the percentage dissolved and what is the percentage that is precipitated out, right. So as you can see here, almost, not almost, the 100% of Fe2 plus is in the soluble form, as in it is either as Fe2 plus which is soluble or the other complexes which are still soluble, right. So keep in mind that at 1.5 millimolar concentration of Fe2 plus, there is no precipitate formed even when we specified that I think a form of FeOH twice, the amorphous form is a possible solid, right. So now let us try that out with the Fe3 plus, let us see. So back to main output menu, input menu, I am going to let us say delete these components, right, and I will still fix the pH at 7. So now I need to put in Fe3 plus, let us see where we have Fe3 plus, okay, we have Fe3 plus here and 1.5 millimole, right. So what is it that we are trying to do here? So if I have FeCl3, right, FeCl3, and that is my initial recipe concentration, how do I plug it into Vimitech? So I need to plug in Fe total and Cl total, right. So obviously that is going to be equal to Fe3 plus total and Cl total, I guess, 3 times, or just FeCl3 not, but obviously what is Cl total here? It is 3 times FeCl3 not, and that is equal 3 into 1.5, which is 4.5 millimolar. This is nothing but based on your formation equations and then writing up your tableau and so on, right. So Fe total, what is the source? It is the source is the FeCl3. So I need to plug in Fe total 3 plus as 1.5 millimolar and Cl total as 4.5 millimolar, right. So let us plug in this millimolar concentration is set, right, add to the list, and then Cl. Cl, and I need to plug that in as 4.5, right, and 4.5. Okay, add that to the list, and again I am going to specify relevant possible solid phases. Right here again, because I limited it to those species that can be formed, I can get what do we say, screened forms of Fe3 plus that can precipitate out. So in general here, as you see, Fe3 plus can precipitate out in different kinds of forms. So we are going to discuss the relevant stages later with respect to precipitation and how they are relevant. But here for now, let's look at ferrihydrite, which is usually the first form that's formed, right? Okay, and back to main menu, and page 7, view edit list, and everything seems fine, and I am going to run Mintech. So again now let us look at what we say species distribution. So most of it is as a complex, most of what now, Fe3 that is in the dissolved form, whatever ferric iron is in the dissolved form is mostly present as a complex, right. So but does that give you the true picture? Not really. Why is that? If you look at the equilibrated mass distribution, you see that Fe3 plus, right, 100% Fe3 plus or almost 100% I guess, right, is precipitated out. Makes sense hopefully. So only a very little form or little amount is in the dissolved form. What is that now? That is 2.9 into 10 power minus 10, and keep in mind that we put in Fe initially at 1.5 into 10 power minus 3. So almost 7 orders of magnitude difference, or 10 power 7 times lesser, is in the form of what do you say, a dissolved form, and that is why almost all of it, right, which this particular Mintech is considering as 100% has precipitated out. And in which form has it precipitated out? In the form of that ferrihydrite that we just discussed. So again let us come back to what it is that we are discussing, right. So let us move on to our particular system here. Okay, so let us see why is this relevant now. So keep in mind that earlier the what do we say, the CETP personnel was putting in or plugging in Fe2 plus, right, and we see that with Fe2 plus, right, most of it would stay as Fe2 plus, right, 85%, and almost all, not almost, 100% is soluble. Let me write it down here, Fe2 plus and Fe3 plus, 100% is soluble, and 85% of that particular soluble species are present as Fe2 plus, right. But with Fe3 plus we see that almost all of it, 100% has precipitated out, right. At pH what is it now, 7 anyway, which is more or less within the ballpark of the pH that the people at the CETP try to maintain, right. So let us look at why this is relevant now. So in general, how does coagulation occur now? Coagulation, right, there are different mechanisms. The first mechanism is charge neutralization, let us say, right. Again that is self-explanatory I guess. Charge neutralization as in your suspended particles or colloids, people presume that they have a negative charge, right, that is a good enough presumption actually, right, and even in the industrial wastewaters people presume that. Again I am saying people presume that, but it can vary. There are sometimes cases when you have the colloids with a net positive charge rather than net negative charge. Anyway, charge neutralization as in you add the counter charge. So if the colloids are negatively charged, right, let us say this is my suspended particle with negatively charged, and right, two negatively charged colloids, repulsion here, right. So that is why I add the coagulant which can neutralize this particular negative charge, right, allowing the particles to form colloids, let us say, right, and that is one particular simplistic way of explaining charge neutralization. So which one would work better in that case if charge neutralization was the principle involved here, Fe2 plus, right. But for industrial wastewaters that is not always the case though. What happens is, you coagulation, you have other mechanisms as in sweep coagulation, right, or sweep flock let us say, as in the precipitate form from addition of your particular initial coagulant which is Fe3 plus, let us say, forms a kind of a mesh, right, FeOH thrice let us say, forms a kind of a mesh, and as it settles down, it can capture or encapsulate the relevant suspended particles too. That is one particular case. But more importantly though, we have co-precipitation. So, people mistakenly call this coagulation, but this is not coagulation, right. This is the principle involved, it is co-precipitation. Why are we calling it co-precipitation? As in when you add Fe3 plus, you see that it can precipitate out in the form of FeOH thrice, almost all of it, right. So, these particular sites of solid Fe3 plus act as sites for adsorption, right, or for the other suspended particles to be formed or agglomerate on this particular solid. Makes sense hopefully. So, they as in FeOH thrice, the solid that is formed when you add Fe3 plus, source of Fe3 plus to your solution at pH 7, which we just saw is 100% precipitating out, right. It will act as an adsorbent, let us say, right, for the other relevant particles, right. So, that is why we call that co-precipitation, let us say. Makes sense hopefully, but people mistakenly call that coagulation. Keep in mind that there are different principles involved here. So, but can Fe2 plus play the role of what do we say for sweep flocculation, right, or co-precipitation now? No. Why is that? It can't form precipitate. We see that 100% of it is in the soluble phase, but that is why if the CETP personnel had what do we say put in the source of Fe3 plus rather than Fe2 plus, he could have had sweep flocculation and also co-precipitation, and turns out for industrial wastewaters that he was receiving, it was not charge neutralization that was relatively important, but co-precipitation was the relevant mechanism that was leading to the removal of the relevant particles here or decreasing his particular turbidity, let us say. So, but what was he doing there in that case? He could not differentiate between Fe2 plus and Fe3 plus and the relevant mechanisms involved. So, obviously he did not have, let us say, the relevant background with respect to the complexation or the precipitation. So, he just plugged in Fe2 plus, but that ended up adding to the turbidity, because for his industrial wastewaters charge neutralization looks like was not an important what do we say mechanism for coagulation and the relevant flocculation. Yes, it was sweep flock, formation of the sweep flock, and more importantly co-precipitation. So, obviously for that particular aspect, what do you need to have? You need to have a source of precipitate, and how can you get that? From your Fe3 plus addition, which can form your FeOH thrice solid, right. So, again I guess I am just trying to link why I guess, right, you need to learn the aspects that we are learning to what you would see out there in the field, right. So, anyway, I think we are running out of time. So, with that I will end today's session, and we will look at a few more applications in the next what do we say session, and then we are also going to move on to look at kinetics and equilibrium, right. So, kinetics plays an important role here, because solid formation, as maybe you might have observed in nature, is not as fast as you would presume for acid base or complexes now. So, in this particular case of precipitation and dissolution, we are also going to consider the aspects related to kinetics and obviously related to equilibrium too, right. And another aspect we need to consider is that, if you remember, for Fe3 plus you saw that there were different types of solids formed, right. So, precipitation occurs in stages, as in initially one type of solid is formed, then the other type of solid, and then the other type of solid, and so on. I mean, mostly only one solid predominates, right. So, that is called a controlling solid, and that determines the concentration of the metal or the ligand in solution. So, we are going to discuss these aspects in the next classes and see why they are relevant again, and I guess with that I am done for today, and thank you.